Hi everyone, welcome back to second lesson on electric field. I hope that everyone had gone through the previous recorded lesson and got the basics of Coulomb's law and its applications. Dear all, before starting a new topic, I would like to recap the main concepts learned in lesson 1. We have started with point charges. We know that it has a finite charge only. Its mass is negligible. Electrically charged particles attract or repel each other even if they are not actually touching. So in this lesson we are going to learn how is this possible. How can they interact without a physical contact between them? Coulomb's law. Coulomb's law gives us the exact size or magnitude of the force between 2 point charges. According to the law, the magnitude of the force is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. That is, F is equal to K times Q1 Q2 over R square. We know that Q1 and Q2 are the respective charges and R is the distance between their centers. K is Coulomb's constant. We have an equation to calculate Coulomb's constant. It is 1 over 4 pi epsilon 0. The epsilon 0 is the permittivity of free space. Its value is 8.85 times 10 to the power minus 12 Fermi per meter. And the final value for Coulomb's constant is 8.99 times 10 to the power 9 Newton meters square per Coulomb square. Later we have realized that Coulomb's law is an inverse square law. What does it mean? The magnitude of the force is inversely proportional to the square of the distance between the centers of the charges, which means as distance increases, magnitude of the force is decreasing. F into R square is a constant, or if you want to verify inverse square relationship, we use F1 R1 square is equal to F2 R2 square is equal to a constant, and so on. And later we have learned the graphical representations of electrostatic force against distance graphs. There are 3 graphs and all those 3 graphs are important and we know how to plot those graphs also. On this slide you can see the objectives of today's lesson. By the end of this lesson you will understand electric field as an example of field of force. You will learn the definition of electric field and how to calculate the field strength. The second objective is the representation of electric field using electric field lines. And the last objectives of today's lesson is uniform electric field and its properties. And finally, as usual, I will introduce typical exam questions that usually come for the exams. Dear students, there are 4 fields in physics. They are magnetic field, gravitational field, electric field and nuclear field. The term magnetic field is very familiar to you. As you know, it is a region or space around a magnet where another magnet experiences a force of attraction or repulsion, which you have already learned in previous classes. Gravitational field of Earth is also familiar to you, right? The region around the Earth where other masses are experiencing a force. So we can use these two known concepts to develop the meaning of electric field. Dear students, we know the fact that even if there is no physical contact between two charges, there is a force of attraction or repulsion. An electric field is a useful concept to help us describe electrical forces, which means forces that act on charges. Look at this arbitrary region in space around this positive charge. If you bring a negatively charged electron or a positively charged proton into this field, that would experience an electrostatic force of attraction or repulsion. Depends on the charge of the particle that you brought into this region. That is, similar to the magnetic or gravitational field, there is a region in space around this charged particle where another charged particle experiences a force of attraction or repulsion. That region is what we call electric field. So, it's a region around a charged particle where another charged particle experiences a force of attraction or repulsion. Michael Faraday developed the concept electric fields. Before starting further discussion on electric field, let me introduce source charge and test charge. For any field in physics, like gravitational field, magnetic field, or nuclear field, we need a source to produce the same. A mass is the source for gravitational field. A magnet is the source of a magnetic field. Similarly, to produce an electric field, we need a charge. So a charge that produces an electric field is called source charge. And if you want to investigate the properties of an electric field, we need a point charge. So a point charge that we are using for this testing purpose is what we call test charge. Dear students, here we have an electron and I have taken a small portion of the electric field produced by this electron. Let us consider 4 different positions in this electric field. Consider we have placed unit charge plus 1 coulomb charge at position 1, 2, 3 and 4. What do you think about the magnitude of the force acting on these charges? Are they same? Yeah, as you think, the magnitude of the force would be different at these 4 different positions. This difference in the magnitude of force is due to the difference in the strength of the electric field around the electron. So electric field strength is defined as the force per unit positive charge experienced by a test charge placed at that point. Students, next we are going to derive an equation for electric field strength at this point x, which is in this electric field. For that, let us assume a positive test charge which has a magnitude q placed at this point x. Let F be the force acting on the same. According to the definition, electric field strength is the force per unit positive charge. So E is equal to F over Q. This is the equation for electric field strength, which will be given to you in the data sheet. Here is the unit for electric field strength from this equation, or we have one more equation or one more unit, which is volt per meter, which we'll be discussing later. Electric field is nothing but the force acting on a charged particle in a region. So it is a vector. Electric field is a vector quantity. If so, what would be the direction of that vector? The direction of electric field would be the same as the direction of force acting on a positive charge placed at that point. So far, we have learned about what is electric field and how to find the strength of the electric field. So now the next question is how to represent an electric field. We cannot take a direct photograph of an electric field, right? So we should have certain ways to represent an electric field. We use electric field lines to visualize an electric field. These field lines are imaginary, but what is represented by the field lines, that is electric field, is a real one. An electric field line is the path followed by a positive test charge placed in an electric field if it is allowed to move freely. Let me make it clear. If an object experiences a resultant force, it starts to move in the direction of the force, right? Similarly, we know that an electric field is a region where a charged particle experiences an attraction or a repulsion. If you place a positive test charge in an electric field, it would definitely experience a force and it starts to move in the direction of force. If you trace the path taken by that positive test charge, that would be representing an electric field line. That's a concept mentioned here. Next, we are discussing about properties of electric field lines. Electric field lines originates from positive charge and ends on negative charge, or in other words, they are directed away from positive charge and directed towards negative charge. Look at this electric field pattern. This is the pattern around a positive isolated charge. If you place a positive test charge at this position, look, since the source charge and test charge are positive, there will be a repulsive force on the test charge so that it starts to move in this direction. Similarly, if you place a positive test charge here, it would take this path, here it would take this path, and so on. That's what I told you. Electric field lines are the path taken by a positive test charge if you allow that positive charge to move freely. This is the field pattern around a negative isolated charge. If you place a positive test charge here, that would experience an attraction towards the negative charge so that it would move in this direction. Look, all these field lines are towards the negative charge. So we can generalize that it seems electric field lines are directed away from a positive charge and they are directed towards a negative charge. Second property of an electric field line is any tangent drawn on this electric field line will give you the direction of electric field at that point. Suppose this is representing an electric field line. Its direction is from bottom to top. If you want to know the direction of electric field at point M, draw a tangent at that point. Direction of this tangent will give you the direction of electric field at point M. If you take another point N, and if you want to know the direction of electric field at that point, you have to draw another tangent. Here this tangent is giving us the direction of electric field at the point N. According to this diagram, it is very clear that in this electric field, the direction is different at the point M and N. Dear students, field lines never cross each other is the third property. Let us assume that two field lines are crossing each other. Field line X and field line Y are meeting at the point O. To get the direction of electric field at the point O, we can draw two tangents, one on X and the other one on Y. According to this, we get two different directions for electric field at the point O, which is impossible as electric field is a vector quantity. So such a situation will never exist. So final conclusion is field lines are not crossing each other. Fourth property is about the strength of the electric field. Number of field lines passing normally through an area is directly proportional to strength of the electric field, which means density of the electric field. Look at this. If you compare these two diagrams, density of electric field lines is higher in the second diagram, which shows that the second one is representing a stronger electric field. Similarly, these two fields, the first one is weaker than the second one. And the last property is field lines never pass through a conductor. Electric field configurations. Here you can see electric field configuration in different situations. These diagrams are self-explanatory. We have already explained about electric field pattern around a positive charge and around a negative charge. If you have two opposite and equal charges, the resultant field pattern would be like this. If you release a positive test charge here, it experiences a push from positive charge and an attraction towards negative charge. So this is the path followed by the positive test charge. So the field line is straight in the middle, and if you release a positive charge here, it is being pushed away by the positive charge, at the same time attracted by the other one. So all these field lines are representing the path taken by a positive charge released in this field, in this combined field. Similarly, these two are representing field pattern between two identical opposite charges. Here you can see electric field pattern between two parallel charged plates. The left plate is positive, right one is negative, and as you know, field lines are directed from positive to negative. Here field lines are equally spaced, and on both ends it is slightly curved, and these diagrams are representing the electric field configuration between a point charge and a charged metal plate. Neutral point. Consider this field configuration between two opposite and equal charges. Let this is a positive test charge placed at the middle of these two charges. Since it is equally away from both charges, magnitude of the force due to the left and right point charges are equal, and the direction of force on this test charge due to the left one is to the right, and due to this right one is to the left. Since force is a vector and the magnitudes of forces are equal and opposite, we get zero resultant force at this point. According to the definition of electric field, an electric field is a region where a charged particle experiences a force. Since this test charge is not experiencing any force at this point, we should say no electric field is acting at that point. Such a point is what we call neutral point. That is, a neutral point is a point where resultant electric field is zero.